system. Distillation depends obviously on heat, and a lot of people focus on heat, but the cooling is very important because obviously we have to condense those vapors into a product. And typically what you'll do in a system like this one is you'll hook up the cooling system to, say, a municipal supply or well water, or you might use a very large radiator, kind of like the hacked computer system radiator cooling system that we use for our lab benchtop unit. The problem with that kind of cooling source is it can vary in temperature depending on the air temperature in the room with a radiator or the time of the year when you've hooked this up to a municipal supply. By varying the water temperature, we vary the water cooling even though you have a continuous flow of liquid. And because of the importance of adjusting the reflux condenser precisely to get just the right amount of folding of our reflux cycles and some pass through a vapor, if the temperatures are varying through the process, you're going to be chasing the valve setting on the reflux condenser, and you're going to be less efficient in terms of capturing the liquid. What I came up with, which I've never seen anybody else do, I think it's kind of clever, is I took advantage of the fact that we have this chest freezer over here. And we'll get a shot of this inside. But what this chest freezer consists of is an inner aluminum liner with the cooling coils. And I took a little bit of Flex Seal and sprayed it on the joints between the aluminum, turning this into a watertight container. And then I filled this with about 110 liters of fresh water and turned on the chest freezer a couple of days ago. And what happens is it begins to freeze water along the cold surfaces of the inside of the chamber. And after about 2 days, I've frozen about half of the water. So I've got ice around the sides, and I've got an inner area in the middle here that contains just water. What's nice about this is as heat is poured out of this unit into the cooling system, the water temperature doesn't change. We simply melt ice and we retain exactly 0 degrees centigrade water continuously through the process. And with about half of the water in here frozen and half as water, we have enough cooling sink in this unit that even though the unit is now turned off, we could run this for about 6 hours, about 3 times as long as you would during any normal distillation, on just the cooling water that's in here. So I don't lose too much product in terms of vapor. I'm going to hook this up and I'll show you how this works in real life. So we got our input here, which is this tubing, and we're going to connect this to a pond or aquarium pump. And then we're just going to sink the pump into this center section where the water is, and then take the 2 output tubes from the reflux and the main condenser and just drop them in there. Then we're going to plug this in and send the water going through the system like this. Meanwhile, what I'd like to talk to you about, though, is these. These are kind of interesting. This is called a bubble plate, and what it consists of is a copper disc with these little crenulated caps that are mounted on top of similar little stubs that are brazed onto the surface here. And the way this works is pretty interesting. On the bottom, vapor is able to pass through these holes and up through the top surface of this plate. Once the vapor rounds the top of this inner cylinder, what happens is the vapor is then forced down through the gap between the cap and between these little crenulated openings on the bottom of each of these caps, and will bubble out. As it does so, the bubbling will allow some of the cooling process to occur and will begin to develop a layer of liquid, as you can see here, above each one of these plates. That liquid will continue to rise until it reaches the top of this little stub here and then pour down into a mirrored cap on the bottom here. This cap also has a stud on the bottom and allows the liquid to fill this cap until it reaches all the way to these little holes here where the liquid begins to drop out. What's elegant about this is it's sort of a one-way valve for liquid and gas. Because of the gas that's coming out of here, the liquid is not able to run into these caps. And because of the liquid layer here, vapor is not able to come up through here. So the vapor is able to come up through these holes and the liquid is able to come down through these holes. And then each of these bubble plates will develop a layer of liquid above them that actually accomplishes the reflux action in a liquid phase rather than a solid. In the Vigreau column, we depended on the surface area here to provide the cooling of the vapor and the extraction of the water molecules to concentrate the alcohol. In this case, where the actual reflux is occurring is on the inner walls of each of the bubbles. As this cooler liquid here sees this hotter vapor, it will extract from those bubbles a small amount of that water which accumulates in this layer of liquid here. And so the reflux or the concentration is actually occurring in the bubble, not on the surface of the glass. Now you can see this continually moving up here, and you can see the dripping coming from each one of these small little stubs here as the vapor is going up toward the reflux condenser. You can see the temperature up here right now is running at about, 78.8 degrees. We don't have enough vapor up here at this point to have heated the thermometer, and therefore we're not getting any output here. Another thing that I want to bring up about this bubble plate is the fact that you notice, unlike the entire structure here, which is built out of stainless steel, this is made out of copper, and there's a reason for that. When you ferment any kind of a grain or any kind of a fruit, you will produce a very small quantity of hydrogen sulfide. And hydrogen sulfide is kind of interesting. If you've ever been in a chemistry lab and you smell that stinky smell that smells so smelly, that rotten egg smell, that's hydrogen sulfide. Hydrogen sulfide is almost as toxic as hydrogen cyanide, and in very, very small quantities will create a foul, sort of rotten smell or taste that will get into your final product. And because of the fact that it is a nerve toxin, at very low concentrations you can smell it. But when the concentrations rise high enough, it will actually anesthetize the olfactory nerves and you won't be able to smell it anymore. So as long as it stinks, it's safe. But once you can't smell it anymore, that's when it becomes dangerous. That doesn't really apply here, but it's an interesting material. And how the copper interacts with this is that hydrogen sulfide is absorbed by the copper. It forms copper sulfate on the surface, and hydrogen gas is released. So the copper will actually convert the hydrogen sulfide to something that sticks to the copper plate and removes that flavor. So even when you're using a stainless steel still, you'll always want to have some copper in intimate contact with that vapor in order to absorb the hydrogen sulfide. So when you have a still that doesn't, say, have a complex reflux column like this, you may make it out of copper. That's why they use the copper in the alembics. And also, if you don't have any easy way of adding the copper in a pipe, you can actually place copper mesh or copper tubing, something inside of the column that has contact with the vapor to get rid of the hydrogen sulfide. Now, as this continues to boil, we can see that the temperature moved from about 78 degrees to about 84 degrees as this is continually filtering water. This water coming out of here is now quite warm, and so this unit up here is doing some reflux cycling, but not very much. And when this temperature pops up to about 150, which it will do in about 2 or 3 minutes, we'll start to see some of the output coming up here. Now you can see that the temperature is rising pretty quickly. We're up at about 141 degrees Fahrenheit, 160. Now you can see that the temperature is rising. It's up at 162 degrees Fahrenheit, and you can see we're starting to get some drips down here. So we're getting output. So I'm going to close this valve, and now we'll begin filling this inner chamber in here and looking for an overflow that occurs up here where we can then make our specific gravity measurement. This will take a minute or two. So if you see here, we have a temperature of 170.0 degrees Fahrenheit. And if you look here, you'll start to see that the liquid is reaching the top and beginning to overflow into this conical section here, and then it will soon begin to pour out through the spigot. I can then take advantage of that convenient cylinder, and I'll drop in my hydrometer. And you can see that what we're looking at right now is about 180 in terms of proof. Now, if we slow this down, we can obviously get higher concentrations. If we add another bubble plate, we can obviously get higher concentration, put it back in other words. Or if we turn our deflegmator or reflux condenser to a little bit more aggressive refluxing, again, we can increase the concentration. But over time, this will continually rise as more and more water is added to the final output. Now, the concentration of this in here, as I said, is about 180 proof. And what's nice about this is frosty cold. Because we are using 0-degree temperature water to cool off this, this is ice cold. And so the product that comes out of here is frosty. As a result, rather than being tepid or room temperature, the very volatile alcohol is less likely to evaporate into the air by using super cold water to do the cooling. It's a big advantage.